Hello students, welcome to this lecture in which we're going to continue to develop rules for the derivatives. Let's quickly go through the rules that we already have. Derivative of constant is 0, derivative of x is 1, derivative of x squared is 2x, derivative of 1 over x is negative 1 over x squared. Derivative of the sum, actually difference would also work, so if you put a minus, it would also be fine. So plus or minus, right? And the last rule is if we have a cake, which is a constant times the function, then you can take the constant out. So the next rule we're going to talk about is the square root. So let's do this. We'd like to develop the derivative of a square root. If f of x is equal to the square root of x, then f of x is differentiable, and f prime of x is equal to 1 over 2 square root of x. So let's try to establish this rule. What would be the proof for this idea? Again, we don't have anything except the definition, so it's going to be the limit when delta x goes to 0, f of x plus delta x minus f of x divided by delta x. We have limit delta x goes to 0. Now we take x plus delta x and we plug it in for this x over here. We will have, not this x, sorry, this x obviously. This is what we want to show. So we'll have a square root of x plus delta x minus from here, then f of x. And f of x is square root of x. And we divide by delta x. So if we try direct substitution, it wouldn't work because we would get 0 on the bottom. Next logical step is to what? Multiply by the conjugate, right? Like we discussed before. And let's do this out. So we take the numerator, x plus delta x minus square root of x, and we multiply it by the conjugate, which means we're going to take the same expression, but we're going to switch this minus into a plus. So it's going to be x plus delta x plus the square root of x, but since we did it to the numerator, we have to do the same to the denominator. So we have this. Now we multiply the numerator, and we have a minus b, and we have a plus b. So it's a difference of squares. And so that's going to be first expression squared. So it's x plus delta x squared minus the square root of x squared divided by the denominator, which we keep the same as before. So we've done this part. We take the square root, we square it. So square root squared is just the expression inside. And we get x plus delta x minus, and square root of x is x, divided by delta x times parenthesis x plus delta x plus the square root of x. So we can clearly see that this x is with the plus and this x is with the minus, so we add them up. We get limit delta x goes to 0. Delta x is the only thing left in the numerator. We have another delta x in the denominator, and we have our big parenthesis here. So that's what we have. Now, we've done it many times, but still, can we divide by this delta x? Sure, because delta x goes to 0 means it's not going to be 0. And we're almost done, except the last step. So in the last step, delta x goes to 0, we're left with 1 over parenthesis square root of x plus delta x plus square root of x. So we can use direct substitution. This term goes to 0. So we have 1 over square root of x plus the square root of x. So we're done with the limit. The only thing left is to add up these two square roots. So we're going to get 2 square root of x. Let's see if that's the same what we wanted. Yes, that's exactly what we wanted. So we're done. So check mark. So we proved this rule, and can we do a short example? Sure. If someone asks us to do this example, find the derivative of f of x, which is equal to the square root, x squared minus 3 square root of x. So what would be the solution for this exercise? The solution would be, we want to find derivative, so we write it as x squared minus 3 times square root of x with a derivative sign. We split it up because of the minus, and we have a constant up front, so it's gonna go out, and we have square root of x with a derivative sign. So I use two rules at the same time, plus minus rule and constant multiple rule. So now I evaluate my derivatives. So I get 2x minus 3 times 1 over 2 square root of x. Maybe it would be nicer to write it like this. So this would be our answer for this problem. Any questions about this one? I think we're pretty good. So we can take this rule and we can add it to the library of the rules that we already had. All right. So what is the next thing to discuss? The next thing to discuss is power rule. Power rule says the following. So power rule. And power rule, we're going to come back to it a couple of times when we're going to develop ideas. So first power rule is the following. If f of x, first iteration of the power rule. If f of x is equal to x to the n, where n is equal to the natural number, and by natural number we mean numbers like 1, 2, 3, 4, 5, all right, like 1, 2, 3, 4, dot, dot, dot. All right, so they're positive integers pretty much. So then what we can say is the following. Then f of x is differentiable, and f prime of x is equal to n times x to the n minus 1. Okay, so maybe later we will prove it. Proof will come later when we learn a little bit more. So let's do a few examples. So our famous rule that we had before, like x squared, we can use this rule now because 2 would fall into here, so it's going to be x squared. So according to this rule, we can take 2, put it down, and write it as x to the 2 minus 1. And if we subtract 2 and 1, we're going to get 2x to the 1, but it's just 2x, right? So we can do it a little bit quicker now. And how about 13x to the 5? If you take derivative, it's going to be 13 comes down, and we have to find derivative of x to the 5. And for x to the 5, we can use this rule, n will be 5. So since n is equal to 5, we take it, we put it down, and we multiply by the x to the 5 minus 1. So 13 times 5, 15, 15, 65 times x to the 4. So that's how this power rule will apply. But so far it only works for the integers, but then we'll try to modify it and make it to work for a lot of different numbers. So we're going to come back to it later. And one discussion that we might have is how the continuity that we discussed before is related to the differentiability. So one thing to discuss is the first example we're going to do is our absolute value of x function. Absolute value of x function. So if it's our candidate, we can clearly look into this function. And this function has this V shape with a sharp point on the bottom. So since it has a sharp point, no derivative at x equal to 0. Now the next question is absolute value of x continuous at x equal to 0. Right, so in order to show that it's continuous at 0, we want to show. So what do we want to show? We want to show that the limit when x goes to 0 of f of x is equal to f of 0, right? So let's try to do that. So we'll have limit absolute value of x when x approaches 0 is equal to, by direct substitution, absolute value of 0, which is 0. And this is also equal to f of 0. So check mark, the function is continuous. So we claim that is continuous at x equals 0, but is not differentiable at x equals 0. So this is an example of the function that is continuous but not differentiable. Right? Any function that has a sharp point will be like that. Any function that has a sharp point will be like that. All right. So we will try to actually prove the opposite of this. Not the opposite, but the reverse, which says that if function is differentiable, then f of x is definitely continuous. So that's our goal for the next discussion. So theorem says that if f of x is differentiable at x equal to x sub 0, then f of x is continuous at x equal to x sub 0. So if function is differentiable, it implies that it's continuous. So we can say that differentiability implies continuity. But not the other way around. If function is continuous, it's not necessarily differentiable, like we saw in the previous example. Okay, so we add the page. So let's try to show this theorem. So what would be our proof? So what do we want to show? We want to show that given f of x is differentiable at x equal to x sub 0, then limit of f of x when x goes to x sub 0 is equal to f of x sub 0. And this is from the definition of continuity. All right, so let's start. F of x is differentiable at x equal to x sub 0. What does it mean? It means that the limit when delta x goes to 0 of f of x plus delta x minus f of x, actually here we can put x sub 0 and x sub 0 because we know the particular point, divided by delta x is equal to f prime at x sub 0, and this limit exists because our function is differentiable. We know that this limit exists. So what we're going to do, we're going to multiply both sides by limit of delta when delta x approaches 0. And delta x is really small, so it's not really 0. So this is fine. So what do we get if we do that? We're going to get that limit of delta x when delta x approaches 0 times the limit of f of x sub 0 plus delta x minus f of x sub 0 over delta x when delta x goes to 0. And look, this part and this part are the same. And on the right side, we're going to get limit of delta x when delta x goes to 0 times f prime at x sub 0. All right, but since we have a product of two limits, we know that we can put them together. So we will get limit when delta x goes to 0, of delta x times f of x sub 0 plus delta x minus f of x sub 0 divided by delta x. So we combine this term together with this term on the left side. And on the right side, since this is a constant, we can always take the constant and bring it inside of the limit. So we'll have delta x times f prime of x sub 0 when delta x goes to 0. So let's look what we get. This delta x and this delta x we can divide. And here, by direct substitution, if we plug in 0 for delta x, 0 times constant will be 0. So on the right side, we get 0. On the left side, we get limit when delta x goes to 0 of f of x plus 0 plus delta x minus f of x sub 0. But since it's a difference in between, we can split it into two limits. So we have limit when delta x goes to 0 of f of x sub 0 plus delta x minus the limit when delta x goes to 0 of f of x sub 0 equal to 0. But look, if you plug in x sub 0 into function f, this would be a constant, and we know limit of a constant is constant. So this is just f of x sub 0, then the minus, then we have limit of x sub delta x when delta x goes to 0 equals to 0. So we're going to take this term, we're going to move it to the right side. So this is f of x sub 0, move to the right side. Now let's try to see what this is. This is x sub 0, this is some other point x, and in order to arrive to this x, we make a delta x step. Make a delta x of a step. Right, so basically x is equal to x sub 0 plus delta x. Right, so we're going to take this and we're going to put it over here. So we'll have limit of x, and now what happens when delta x goes to 0? When this quantity becomes smaller and smaller and smaller, x travels to 0. So instead of delta x, we can write x goes to x sub 0, and this is exactly what we wanted to show. So, so we're done with this proof. We showed that limit of, oh, sorry, didn't do it right. Small mistake. So here, did not write it correctly. Let me fix it. That was f of x sub 0 plus delta x, right? So it was f of x sub 0 plus delta x. So this should be f of x. So made a small mistake, but gladly I found it at the end. Should be limit of f of x when x goes to x sub 0 equals to f of x sub 0, which shows that the function is continuous. And we started with the differential. So that's good for us. The last thing for today to discuss, not for today, but for this lecture, is to discuss the following rule. Theorem that says that any polynomial function is differentiable. Any polynomial function is differentiable. Why would it be true? Because since f of x equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus ... And the last couple of terms are as follows. And you can clearly see that because of the sum rule, we can split it up into the bunch of monomials. And each monomial is differentiable because of the power rule. So that's why it works, right? So this one is differentiable. This one is differentiable. This one is differentiable. This one is differentiable. And this one is differentiable. So any polynomial function is differentiable. But not only that, you can also say like this. And corollary is a small theorem that is a consequence of some other theorem. So it's like a smaller theorem. This one says that any polynomial function is continuous. Any polynomial function is continuous. Why is that? Because we know that if the function is differentiable, it is continuous by the previous theorem, right? So every differentiable function, scroll a little bit up, every differential function is continuous, right? So probably a good place to stop, and I'll see you in the next lecture, in which we will discuss why power rule is dangerous, and we'll try to talk about product rule.